chlorination of methane is an example of a free radical reaction. We'll explain what radicals are in just a few minutes. But free radical reactions are among the most common chain reactions in organic chemistry. When I say that they're chain reactions, it means that they typically proceed through three distinct stages. The first one is initiation, which is basically the generation of reactive intermediate. So remember, reactive intermediate is one of those B's and C's which takes us from A to D. The second step is the propagation, which is a reaction of reactive intermediate with starting material. And this reaction generates both the reaction product, but also regenerates reactive intermediate. And so reactive intermediate goes into propagation step, reacts with starting material, generates product, and is in turn regenerated, which allows it to go into the next propagation step, and then the next one and the next one. And so the reaction has only, in theory, has only one initiation and thousands, if not millions of propagation steps. And then at the end, the final step is termination, which is sort of the reaction end, which is typically a side reaction that destroys the reactive intermediate. And since reactive intermediate is needed for propagation to occur, the reaction is basically shut down. So in principle, if we start with initiation, then we'll go to one propagation step, another one, another one, another one, and only at the end we will reach a termination. Overall, the chlorination of methane is a substitution reaction. And so when we start with methane and chlorine, the net result is that we substituted or replaced one of the hydrogens on methane with chlorine to get the reaction, which is basically a radical substitution. So let's look now at what these steps, initiation, propagation, termination, are specifically for the example of chlorination of methane. So the first step is initiation. And in our case, this initiation begins with chlorine absorbing light. In previous topic, we mentioned that chlorine is the one that kickstarts the reaction, not methane, because chlorine absorbs light. And what this reaction does is this typically blue light, the energy of which is 58 kilocalories per mole. And what this reaction does is split chlorine molecule into chlorine atoms. Basically, this electron goes back here, and this electron goes back here. Now notice that the arrows that we're using are not normal curved arrows that we used previously, for example, to correlate different resonance structures. These arrows have only one side, so they kind of look like hooks. And these fish hook arrows indicate motion of only one electron. Here we're breaking this bond with one electron going to each atom. So this is not the motion of an electron pair or a double bond, it's just one electron move. And what we're getting is two chlorine atoms, now each one of them has just 7 electrons. Now chlorine, this is our reactive intermediate. And by this point you should be already proficient enough in looking at the octet rule to be able to say that neither of these two chlorines has an octet rule. They have 7 electrons. And furthermore, one of them is unpaired. So unpaired electrons are particularly unstable because they tend to pair up. Such species with unpaired electrons are called radicals. As I already mentioned, radicals are very reactive, and so they never really build up in solution because they can't stick around. So they react almost as soon as they're formed. What we're seeing here is a chlorine radical, but many other radicals exist. For example, a bromine radical is very common. Carbon-based radicals are common as well, so this would be methyl radical. Or an ethyl radical. Or so forth. Now notice that radicals in this case are not charged. They have 4 electrons around carbon, and so this is no positive or no negative charge. But they still are unstable because of this unpaired electron. Okay, so after this initiation occurred, the next step is a propagation step. And so this chlorine radical now roams around and looking for something to pair up its electron with, and the thing that it sees is methane. And it basically steals one electron from this bond, leaving the other electron to go back to carbon, with the overall result being that chlorine now established a bond with hydrogen, but the carbon is left with just a methyl radical structure. Okay, so this is hydrogen chloride, a stable molecule, which is one of our reaction products, but this is a methyl radical, which is not stable. Sorry, methyl radical. Now, methyl radical, again, is unstable, and so now it is roaming around and looking for something to take an electron from, and what it encounters is another molecule of chlorine. So it quickly pairs up with one of chlorine's electrons, leaving the other one to go back to another atom, and resulting in a carbon-chlorine bond here, and this is methyl chloride or chloromethane, our other reaction product, and a chlorine radical. And now we're back where we started, because this chlorine radical goes back and continues the chain. So propagation in our case is really 2 steps. In the first one, where chlorine radical attacks methane, and in the second step, where methyl radical attacks chlorine to regenerate the original reactant. And now you can see how from our previous topic, our second experimental observation makes sense, because we need light only in the initiation step. Once we're here, we already have a reactive species, be it a chlorine or a methyl radical, which doesn't need any more energy in the form of light. It's reactive enough and just keeps going and going. Okay? And so at some point, a relatively unlikely thing happens. And what is that unlikely thing? Well, I told you that concentration of radicals is always very small in the reaction, actually because they react so quickly, so they don't really build up. And so it's unlikely that one radical will encounter another radical. But it does happen. And so once that happens, our chain reaction, our chain propagation is basically killed because it's carried over by the presence of radical. And once we see two radicals next to two radicals see next to each other, they will pair up their own electrons to give this. And this, since we have at various stages in reaction, we have different species in solution, this can be a number of different pairs of radicals. So this can be reaction of chlorine with methyl radical, or two chlorine radicals, or two methyl radicals for that matter. Okay? And so here, the chain reaction is broken. Okay? And so this will be the first step of our description of the reaction. This is the mechanism of the reaction, where we analyze each individual elementary step. We saw what bonds are formed and broken, where do electrons go, and all that. But this still doesn't really, it sort of tells us how did the reaction work, but it doesn't tell us why does it work. Is it energetically favorable or not? Does it need energy input? Does it release energy? And it doesn't tell us how fast does it work. It just tells us how it works. And so, as we mentioned a little bit before, now we'll talk about thermodynamics, which tells us why does this reaction work and what its energy balance is.